running. So I'm hoping that by now, all of you know where to find class material, which is at moodle.losreals.edu, and also where to find the YouTube recording, which is at youtube.com/someprofs. Okay, so you have to go to you have to go to YouTube, and then just add the slash and then some profs at the end of that, and then and then you go to videos. And then it will just show you or list all the recordings using a reversed chronological order. So the last one that we had here is on the 26th, which is correct, I think. Or did I miss one?
28th.
28th? Oh yeah. Okay. So that is the correct one because we met last Thursday, and that was a Thursday. So I can see that there were 19 views, okay, not necessarily from 19 people, but there were 19 views of that video. So that's good. I think most people are kind of getting the hang of where to find resources for this class. So what I'll do today is we'll continue to talk about adding and subtracting, but this time we'll be doing it from the perspective of the logic gates. All right. So according to the notes, this is where we are at. We're at binary numbers, adding and addition and subtraction, and then the next topic is half adding and full adding, which are basically discussions of how to perform addition and subtraction, but not from the perspective of adding and subtracting, which are arithmetic operations, but from the perspective of logical operations, like using the AND gate, the OR gate, and also the NOT gate, the negation gate. Okay? So why do you think this is important? Why are we even talking about this, how to perform addition and subtraction, but without looking at it from the perspective of arithmetic operations, but from the perspective of logical operations? What's inside the computer?
Transistors.
Transistors. And transistors are very small and they're very primitive, devices. So we organize transistors into what is the next level of construct? Gates. Right, exactly. Okay, so each gate is basically, it can perform a logical function. Just to remind you guys, what a gate is, there are 3 types of gates that you should know already. We don't call those gates in cisp310, we call those operators, or logical Boolean operators. So what I'm going to do is to use a little notepad here, as if it is a whiteboard. So this way, everything is recorded. So I'm going to change the font, make it a little bit bigger, so this way everybody can see it. Okay, so here's my little whiteboard. There are only 3 gates that we really should know at this point, and everything else can be derived from these 3. Okay, the first one is a conjunction, also known as an AND gate. Okay, how do we define the AND operation? There are how many combinations? Okay, first of all, what can appear? Okay, so if you look at an AND operation in C and C++, which is the ampersand operator, what can be on each side of the AND operator? True, false, okay? Which is Boolean, okay? Now in C and C++, it's kind of misleading because you can have anything on either side. You can even have a pointer on one side. But when it is interpreted, it's either 0 or non-zero. A 0 is the same as false, and a non-zero is the same as true. Exactly. Okay. So there are 4 possible combinations, which is true, and true is defined to be true. True and false is false. False and true is false. And then false and false is false. Okay, that's how we define the conjunction or the AND operator. The OR operator is defined similarly, except this time I'm going to use a quicker and easier representation. We have an independent variable x, and then we have another one called y. And then we want to define x or y. In C++, it is a double bar, vertical bar to represent logical OR. True, x can be true, can be false. When x is true, y can be true, y can be false. When x is false, y can also be true or false because these two variables are independent. The definition of OR is defined to be true or true is true, true or false is true, false or true is true. False or false is the only time you get a false. Are there any questions about the representation here? I'm just using two different ways to define the OR operator and the AND operator. I'm hoping there's nothing new here because this is really, really important stuff. Okay? And then we have one more. The last one is easy. The last one is x and versus not x, the negation of x. When x is true, not x is false. When x is false, not x is true. Okay, so these are the only three operators that I expect everybody in this class to know already at this point. Are we still doing okay so far? Okay, all right. Now in C and C++, these are operators. In other words, you can use an expression on the left-hand side, another expression on the right-hand side. As long as the expression can be interpreted as 0 or non-zero, it can be a pointer, can be a floating point number, can be an integer, it doesn't even matter, okay? But as long as it can be 0 or non-zero, it can be interpreted as Boolean, okay? But inside the computer, we do not have 0 versus non-zero. We have either there's a voltage present or not a voltage present, or it is above a threshold or below a threshold. So we still have true and false, except in this case it is interpreted by its physical characteristics. Are we still doing okay so far with these things? Okay. So the next thing we want to do is to say, how do we translate addition and subtraction into operations like these? Because we want to be able to come up with the logic gate combination so that you can perform addition and subtraction inside the computer, in the processor. Is that making any sense? Okay, so we'll see how we can do something like this. The first thing we'll do is we will kind of review what we talked about last time already, but this time I'm going to do it kind of quickly. So once again, we have two independent variables, let's say x and y. But this time we'll take a look at the result of x minus y. And there are two results that we want to focus on. We want to look at the actual result of x minus y. Well, let's deal with plus first. Okay, I think most people want to deal with addition first. So we want to look at x plus y, and then we want to look at the carry of x plus y. Are we doing okay so far with these four columns? X and y are independent variables. They can be either zeros or ones. X plus y is reflecting what you should get as a result, but without taking the carry into account. The carry is the carry of the entire operation. Are we doing okay so far? Okay. Now, since this is binary or Boolean, x can be either a 1 or a 0. And while x is 1, y can be a 1 or a 0. While x is 0, y can be a 1 or a 0. So now we have the four possible combinations of the input into an addition operation or addition mechanism. Okay. Does everybody understand that x and y are the input to the operation of adding, and then the result is the result of x plus y and also the carry of x plus y. Those are the output of this entire operation. In terms of x plus y, 1 plus 1 is a 0, okay, because it bumps it up to the next digit. 1 plus 0 is a 1, 0 plus 1 is a 1, 0 plus 0 is a 0. And we have the carry column to fill in too. 1 plus 1 is a 0, but the carry is a 1. We are carrying to the next digit. 1 plus 0 is a 1, but with no carry. 0 plus 1 is a 1 with no carry. 0 plus 0 is 0, but without any carry. Are we still doing okay so far with this little table here? The first two columns, x and y, are input, and then the other two columns are our output. The outputs are independent. For the most part, you can just look at those as independent outputs. So now the question is, can we somehow use our logic gates, which are the AND, the OR, and the NOT, in order to come up with the same result as x plus y, and then use another combination to come out as the carry flag? What do you guys think? We can probably do something like that. As long as we can see a 1 as a true and a 0 as a false, we can probably use the gates, to come up with the same results. Are we still doing okay so far with this? What I'll do is I'm going to add another column here. We'll deal with the easy one first, okay? I think the carry flag is the really, really easy one to deal with, because what we need to do is to look at the result of x and y, looking at 1 as a true and looking at a 0 as a false. What is x and y in the first one, on the first row? 1 plus 1, or 1 and 1, which is true and true is true, which is a 1. And what about the second row? False. Third row? False. And the last row is false as well. Woohoo! Right? The AND gate, just by itself, can already implement and give us the correct output for the carry inside an addition. And this is all without using any arithmetic operation. It's just logical operations. The more difficult one is x plus y, okay? Because x plus y cannot be an OR. The OR operation seems like a good start, except on the first row it doesn't work, because 1 or 1 is a 1, but we want it to be a 0. So that doesn't work. So how am I going to fix this? Well, there are several ways to do it. There's no one single solution to this, but one solution is to do it like this. We have something and something here. I'm going to fix the alignment of the other columns later on, but for now we'll focus on this one here. So what we'll do is we'll say x and not y, or sorry, this is supposed to be an or, not an and. The other one is not x and y. All right, so we are now making the table a little bit wider than before. So I'm going to move everything over just to make sure the alignment is still correct. I could have just given you the expression and then say, well, that's the answer, okay, and then move on. But if you have taken classes from me, from at least 1 or 2 classes, you always question what I say. You always ask Tech to prove what he has just said. Okay? So we want to do this. Okay? We really want to prove that this really is the same thing as x plus y, even though it doesn't look like x plus y. It does do the same thing. Let's take a look at the first row. The first row is having x being 1, y being 1. These are the input into the operation. So we have this one being true, and this one also being true. But because the second operation is after the negation, it becomes a false. So now it becomes true and false. True and false is what? False. Okay, but we have a second chance to make the entire thing true because we have a disjunction here. Let's look at the other side. This is true, which means this is false. And this is true. So we have false and true, which is false. So now we have this entire thing false. We have this entire thing false. What is the result of the entire disjunction? It's a false. Okay. So far it seems to be working out okay. Let's take a look at the second row. On the second row, we have x being true and y being false. So if y is false, not y is true, x and y is x and not y becomes true and true, which is true. Now, if one side of OR is true, we don't have to bother to evaluate the other side because it only takes at least one side to be true for the entire thing to be true. So now we can conclude on the second row that we also have a match. Now, because the way we use x and y is symmetric, so that means on the third row it's also going to be a true. So the last row is having x being false and y being false. Now, on this one, since x is false already, we don't have to bother to evaluate not y, because in a conjunction, you only need one side to be false for the entire thing to be false. So now we have this whole thing being false. The same argument applies to the right-hand side of the disjunction, because we have a single y here, and on the last row, y is false already, which means this entire thing is false. So now we have false or false, which is false. False is 0 after we do the conversion into zeros and ones. So now we have another match. Okay, so we have this match of x plus y. Are we still doing okay so far with this discussion? And we have just converted arithmetic operation using plus, in terms of using carry and the result of an addition, into logical operation using and, or, and not. Are there any questions about this part? No questions? All right. Nobody seemed to be, amazed or, feel that this is actually important. But it really is important, because this is the smallest mechanism to perform arithmetic operations using only logic gates. Okay? If there are no questions, what I'll do is I'm going to write this on the board, because I want to draw a picture, just for your reference. I mean, this is not going to be extremely important, but you really want to know how this is represented as a picture. Okay, so I'm going to draw this on the whiteboard. You feel free to take a picture of this using a cell phone or whatnot. Okay, so we have x, y as the input into this entire thing. The carry flag is the same thing as x and y. So the representation of an AND gate looks like this when you draw logic gates. Okay, it's just a little thing. It looks like a D. So x is an input. The inputs are going into the flat end of this whole thing, and then y is also an input into this whole thing, and then the output becomes our carry. Okay, it's just another way to represent the equation, except I'm using symbols. This is called a schematic of gates. The other one is a little bit more complicated, because we know that we have two AND gates here. You may want to wait a little bit until I'm done with this entire thing before you copy it. And then we have an OR gate, to take the result of the AND gate, and then this is my final output. Now the final output, I'll just call this R for the result of an addition. Okay, you can also use S for sum, okay, but I'm just using R for the result of the operation. So we know that the disjunction is taking the output of each conjunction as the output. So this part is easy. But with the first conjunction, we are taking x just the way it is. Right? So we'll just say, okay, we'll take x the way it is. But it's not taking y the way it is, because it's taking the negation of y. When you draw logic gates, the easiest way to negate something is to draw a little bubble. So that little bubble, that little circle here, is representing the negation. So now, with the first AND gate, it is taking x just the way it is, but it's taking the negation of y as an input. Now we can look at the second conjunction, which is taking the negation of x, but the original version of y. So the y part is easy. We just say y feeds into this without any negation. But when we are dealing with x, then we have to use a bubble here to represent we are taking the negation of x. Are there any questions about the picture that I just drew on the whiteboard? There's nothing new in this picture that is not in the logical expression. In other words, we are just drawing the same thing. We're just representing the same thing that we have seen on the whiteboard, on the projector, except this time we look at these things from the gate perspective using a schematic representation. But they're really still the same thing. Any questions? Are we done with the addition stuff? No, this is actually called a half adder. If you look at this entire thing, it is called a half adder. So I'm going to draw a boundary around the half adder itself. Okay? It's called a half adder for a reason, because it only performs half of the operations on each column when you add numbers together. Okay, it doesn't do the entire column, it will do half of it. And then the other half has to be done, well, using about the same mechanism. All right. Are there any questions before we move on? Okay, if there are no questions about this, we'll do a few exercises using, let's say, 4-digit by 4-digit addition in binary. So we'll start with something that's relatively easy. Okay, so we'll start with, let's say, 1011 plus 0110, and we want to look at the result of this. Right? So these are both binary numbers, so we are dealing with binary addition in this case, using the binary rules for adding. The way I'm going to do this is a little bit different from how you would write it on a piece of paper. I'm going to use one row to represent the carry from the previous digit, or from the less significant digit. So, and that will be added to the result of the addition itself to become the final result here. I'm going to scroll up so that people in the back can see it. All right. Sorry. What is 1 plus 0? According to the table, and also according to the schematic, what is the result of 1 plus 0? 1. Okay, very good. And I'm going to dedicate this entire row for carry, or the carry from the less significant digit. Since this is already my least significant digit, or LSB, what is the 0 from the digit that is less significant than this particular column? 0 is an implied 0. Very good. So the carry is automatically just a 0 because we do not have any less significant digits. Okay. Well, now the fun part here is I can do this on each individual row without having to look at the result first. What is 1 plus 1?
0.
It's a 0, and it has a carry. It has carry of 1 to the next digit, right? What about this 0, this 1 plus 0 here? It has a result of 1 plus 0 is 1 with or without a carry. Without a carry, so we can say it's with a carry of 0. What is 0 plus 0?
0.
Has a result of 0, and the carry is already here. We do not override that carry. In other words, there are two ways to bump the carry of the next digit. Okay, it can be from the first addition, can also be from the second addition. Let me re-emphasize what I mean by the first addition and the second addition of each column. This one and this one, that's the first addition. This 0 and this 0, that's the second addition of the same column. And each addition can contribute to the carry of the next column. Okay? If either one is a OR, if either one is a 1, then the carry to the next digit is a 1. Are we still doing okay so far? Okay. Let's finish this one. 0 plus 0 is 0 plus 1 is a 1, and it does not contribute a carry of 1 just yet. Okay, so we'll just kind of leave it blank when it is not confirmed to be a 1. What is 1 plus 1?
0.
It's a 0 with a carry of 1. Then we put a 1 here. And now we have a 1 plus 0 is a 1, and then 1 plus 1 is a 0 with a carry of 1. Okay. Now you can see that I don't put that 1 at the bottom, because when you perform binary addition, you have to say, okay, how many bits am I represent what is being used? Okay, in this case, I'm adding 4 bits to 4 bits with a result of 4 bits. So the extra carry, which is the one next to the cursor right here, this carry here, is not actually stored as a part of the result. It is just a carry flag that is quote unquote floating around. Okay. Are we still doing okay so far with this stuff here? Okay. Question? No. Okay. All right. So if this is okay, then what we'll do is we'll take a look at a general way to organize the input and the output so that we can actually see, how we can utilize the these expressions here to get to the result. But before we move on, I'm going to simplify things a little bit. I'll just say that R, X, Y is defined to be this kind of lengthy expression here. There's no need to rewrite that expression all over the place. Okay, we'll just say R is a function. It takes X and Y as input to the function, and then the output of this function is really the same thing as the other expression that we have seen before. The other one, I know it is really simple, but I'm going to do it anyway, just to be consistent with the other one. So the carry function will also take two inputs and use just a simple conjunction in this case, to calculate the output. Are there any questions about what R and C are about? They're just functions, they're shorthands, so I don't have to rewrite the entire long expression all over the place. Is that part okay? Okay. All right. So if this part is okay, then we'll take a look at a 4-digit by 4-digit addition. But this time we're not going to say 1011. We are not going to use concrete numbers. Instead, we'll say this bit here is called A. This bit here is called, well, I think I have to space out these things quite a bit here. So we'll call this one B, C, and D. In other words, the first number is represented by 4 bits, and the bits are just A, B, C, D. Okay? And I might need more space here as well. And then the second number, the second 4-bit number, is also represented by 4 bits. And I'm going to say E, F, G, H here. So we are interested in the result of A, B, C, D as a 4-bit number plus E, F, G, H as a 4-bit number. So according to the picture from previous here, this one here is the addition of this one and this is 0. Okay? So in here, what am I going to use to represent that result? Using D and H as input, but which function am I supposed to use here? We only have 2 functions. One is the result of an addition. The other one is the carry of the addition. Which one should I use here? R. Just the R. Okay, so we have R, D, H here. Is that making any sense? Okay. What about the carry that is supposed to be matching this particular location here? Well, since this is the least significant digit, it has no carry from any other columns, so it is just a 0 in this case. So if that is a 0, I don't have to go through all the functions and whatnot to find out what is the result here, because I know exactly what it is supposed to be. Because whatever that bit is, R, D, H, it's only adding 0 to it, and it will just get itself back in the end. Okay, so this is not too bad. What about this stuff here? What should take this place?
R.
Exactly. So this one should be R, C, G. Okay. And things are not getting aligned right, so I'm going to have to readjust a little bit. There we go. And also, with this one, same thing, not too big of a deal. So B, F here. I'm just having problems aligning things. Okay, so this one here is the result of adding A and E. There we go. So first row is pretty easy. We just apply R to everything, and we're done. But the second row is not going to be as easy. Okay. In other words, this is going to be quite a bit messier than before. All right. So what we'll do is we'll take a look at this place here, which is equivalent to this guy over here. Okay. So what should this be? CDH. That is correct. CDH. It is the carry of adding bit D to bit H from the less significant digit. That makes sense. Okay. And what about this guy here? How about we call it something else, and then we'll have to kind of peel it off and express it later on. Okay, so we'll just call this, let's see, GHI. Let's call this J, and then we'll define J here. What do you think J should be? J is the result of adding this bit to this bit over here. So what is supposed to be J? Using our function. Right? I'm just copy and pasting. So that gets a little bit complicated. Just a little bit. What about this guy over here? So J, K. So this is bit K. So bit K is supposed to be what? It is representing the disjunction of two carries. It is the disjunction of the carry of this bit adding to this bit, or the carry of this bit adding to this bit here. So it gets a little bit messy when you have to write it out, because it is actually the carry of CG, that's the easy part, or the carry of adding RCG to CDH. Yep. Because either one can contribute to bit K in this entire thing. Am I doing okay so far? Making any sense? Okay. It just gets more complicated. However, it's the same mechanism. Okay, we just have to know, how do we calculate a particular carry flag? Okay, so GHIJK. So this is L. I'm gonna skip L, M, because L and I look like a 1, so I'm gonna skip all of those letters. What about M? Let me show you where M is supposed to go. M is supposed to go here. So from this picture, you can say it is the result of adding B and F. Well, okay, I take it back. It is the result of adding B and F and one other bit. Which other bit are we talking about?
K.
Well, yeah, we can just use K here because we just defined K already. Are we doing okay so far with this picture? Okay. And then we have 3 more bits to go. Okay, this is M, this is N. So let's take a look at N here. How should I define bit N? Bit N is the carry from the previous column. The previous column has 2 ways to generate a carry. It can generate when we add bit B to bit F. It can also be generated when we add this bit to this bit over here. So it becomes a disjunction of 2 possible things. One is, oops, keep forgetting to change the overwrite versus insert. Okay, so it can be the carry of one thing or the carry of something else. The first carry is from adding B to F. The second carry is from adding BF to K. Is that making any sense? Okay. But you can see a general pattern now, right? I mean, you can see that, in order to define the carry bit of the more significant column, we have to take the disjunction of the 2 addition of the current column. What about this one here. I'm going to skip O because it looks like a 0, so I'm going to use P here. What about bit P? It is the result of adding two things. The first bit that we put into this whole thing here will be this particular bit. So we just copy this whole thing here, RAE, and then the second bit is bit N. And then there's one more bit. The one extra bit is the carry flag or the carry bit that is just floating around. It is not stored as a part of the result. I call this bit Q. It is not stored as a part of the result, but yet it is still in the system. We have access to that one extra carry flag, but it's not being stored as a part of the result. Okay. And this is bit Q. So bit Q is going to be the carry of something or the carry of something. It's going to be the carry of adding A and E together, or the carry of adding R, A, E, and bit N in this case. Are we still doing okay so far with this picture? Now, I'm very tempted to turn this into a homework assignment where you just draw the picture using the AND, OR, and NOT gate and for a 4-bit adder. It looks like it's going to be kind of difficult, but it's not. Okay, if you define your structures correctly, this is actually not too bad. I can draw this picture not using just the AND, OR, and NOT gates, but using the construct of a half adder and then a full adder. Then it won't take much time. So let's take a look at this at the whiteboard here, and let's see what we can do with this picture. So this is a picture that shows the inside of a half adder. In other words, if you look at this entire boundary, this is a single half adder. It only does adding, but half of it, not the entire thing. Okay? So you can basically look at a half adder. So sometimes I draw a half adder in the opposite way, which means I have X and Y coming in from the top, and then we have the output of carry coming out from the bottom, and also the result coming from the bottom. Okay. The first column using DH and a 0 looks kind of like this, right? Because this result here goes all the way to the end of the entire the first column, and this becomes the first column of the addition. Is that okay? But the second column gets a little bit more complicated. The second column is going to have two half adders because it has to, let me just relabel things a little bit here. I'm going to change the XY to the right labeling, which is DHU. Okay, so we have D and H being here. The second column starts with a half adder that takes the inputs from bit C and bit G. Okay? The result of the half adder, which is RCG, is here. And then the carry of adding C and G is here. But we are not done yet, are we? Because we have to take the carry of adding bit D and bit H and perform another half adder. So we have another half adder here. The other half adder is taking the result of adding bit C and bit G as one of its input, is taking the carry of the previous column as the other input. Are we still doing okay so far with this picture? Okay. And an outcome, it has its own result here. And its own result is just bit J as the output. So this is actually just known as R, D, H in the equation. This is bit J. This is representing the second column of the 4-bit adder. attack, we have two dangling outputs here. The carry of this, of the top half adder, and the carry of the bottom half adder seems to be dangling. They're not doing anything, right? Well, let's take a look at the third one. I'm going to do the third one, and then we'll be pretty much done. So at this point, what I'll do is I'm going to define what a full adder is. This picture has almost one entire full adder, except for one little thing. If you look at the blue column, it is almost a full adder. It's missing just one little thing here. It's missing a OR gate. The OR gate is going to take the carry from the first half adder, and then it will take the carry from the second half adder, and then it becomes the full, it becomes the carry of this entire full adder. So when we combine two half adders, it becomes a full adder. Kind of makes sense, right? Two halves make a whole. Okay. So at this point, what I'll do is I'll define another symbol and kind of use it right away, which is a full adder. A full adder has 3 inputs and 2 outputs. The 3 inputs are 2 bits being the input, and also 1 carry from the previous digit as the input. So this is an input, this is an input, this is an input. It has 2 outputs. It has its own result as an output, and it has its own carry as an output. Does this match the second column, having 3 inputs and 2 outputs? Let's count. Input 1, input 2, those are the inputs from the original numbers, the numbers that we're adding. The third input is the carry from the previous digit. This is the third input. It has 2 outputs, the result itself, and then the carry to the more significant digit. In other words, I am just trying to make structures out of these gates. If you remember in C and C++, you have structures, right? What do you use structures for in structured programming? Well, to create constructs, right? You create smaller constructs, and then you can make even bigger constructs from the smaller constructs. That's exactly what I'm doing here, except I'm doing it with logic gates. All right, so with the definition of a full adder, which is made out of 2 half adders and a disjunction, let's see how we can do this with the third column, or the BF column here. The 2 inputs from the top are bit F and bit B. Okay, they serve as the input, as to the adder. It also takes the output of the previous, carry as the input into here, and in this case, that would be represented by bit K. But bit K is nothing more than, just a disjunction of those things. In other words, I'm just going to highlight this part here. Okay. And then it has 2 outputs. The plain output, which is not the carry, is bit M in our case, in that picture. And then the other one is our bit N. It goes to the next full adder. Are we still doing okay so far with this schematic? And that's how a slow full adder for 4 bits is implemented. And you can see, if I want to add, more to the width of this operation, if I want to make a 32-bit adder, what do I do?
Keep adding full adders?
Yep, just keep adding full adders. So the next full adder will also take the carry of the previous adder as one of its inputs, and then its own output will go to the next full adder. So we can basically just keep stacking full adders to have as many bits as we want. But this is going to be slow. This is going to be slow because each gate takes time to quote-unquote settle. In other words, if you look at a basic, let's say look at this basic AND gate here. From the time that X and Y, becomes stable, in other words, they're no longer in transition, to the time that the output of this AND gate becomes stable, which means it's no longer in transition, there's a propagational delay. The propagational delay is very short. It's only in maybe 1 or 2 nanoseconds. I don't really know how fast these the new transistors can change its state. And by the way, what is the current size of transistors? What is the transistor size of the next generation of Intel processors?
19.
They're coming out. So go ahead.
19 nanometers?
14. The 14s are coming out, soon.
Okay.
Yeah.
But they're not out yet.
They're not out. They're not out yet. But Intel already has the process down for the next generation, which is 14 nanometer.
Aren't we into like 7 millimeter NAND or 7 nanometer NAND?
I do not know, but I think the next generation of Intel processors are supposed to have 14 nanometer transistors, which is really, really small. It's only in 1990 something that people thought that we cannot make a transistor smaller than 1 micron. And how big is 1 micron in terms of nanometers? A lot. 1 nanometer is 1 micron, which is 1 micrometer. So how does 1 micro relate to 1 nano? 1,000, exactly. So it was only about 14 years ago, not 14, 24. So it was about 24 years ago when we thought, 1,000 nanometer is the smallest possible theoretical. It's theoretically speaking the smallest size a transistor can ever be, and now we are at 14 or so. Okay, so 14 compared to 1,000, what is the factor? About 60, 70-ish. Okay. So we thought, 24 years ago, we thought we had to stop at 1 micron, 1,000 nanometers, and now we are down to 14. That really kind of tells you, the history of, how we can make computers faster and faster, and it's all done by, it's still according to Moore's law. How many people know what is Moore's law? I'm digressing a little bit here. What is Moore's law? What is it saying? Just in general.
That processor sizes will be halved every 15 years, 50 years? I can't remember the time frame.
18 months.
18 months? Okay.
18 months.
The hardware will shrink in half.
Yeah, there are several ways to express it. One way to express it is every 18 months, for the same amount of money, you'll be buying twice the processing power. Which if you think about it the first time, it doesn't sound very interesting. It's like, okay, so if I buy another computer for $500 18 months from today, that computer will be twice as fast as the computer that I'm buying today for $500. Okay, it doesn't sound very interesting. But remember, this is all going to compound. Okay, so let's say 24 years ago, 1990, when we thought that 1 micron is the theoretical limit of how small a transistor can ever be. Okay, 24 years is how many months? Okay, I'll put it in another way. How many 18 months are in 24 years? Come on, you guys can do this.
16.
16, exactly, okay? So there are 16 18 months in 24 years. The reason why I want to express it to the number of 18 months is because I want to apply Moore's law directly. Moore's law says every 18 months we double the speed of a computer for the same price, okay? So from 24 years ago to today, how many times would we have doubled the processing speed? 2 to the power of 16. It's not 2 times 16, which is only 32. It is 2 to the power of 16 because it compounds, okay? And that number would be 65,536. So when you pick up a computer from 1990, which is likely to be an i386 EX computer, or SX, sorry. The SX is the first one that came out, which has a 16-bit bus. compared to a computer today, that computer would only be, about 65,000, of the processing speed of a computer today for the same price. No one seems to be amazed. It's like, okay, it's all numbers.
It's gonna get better next year.
Yeah, it'll get better next year, right? Next year is going to be. But this also gives you an equation of, I'm pretty sure some of you put your own computer together, or when you try to buy a new computer, you look at all the latest and greatest, and some people think if I spend more money today, I get something faster, it will last longer, right? That's a fairly common, argument of buying a slightly more expensive model of a computer and think it's going to last longer, okay? But if you look at this equation here, most of the time when you spend more money to get a faster processor, it's not worth it. It's not worth that money. Yep.
Well, by that logic, wouldn't it never be worth it to buy a computer ever?
Well, if you need to use one, you don't have a choice, do you?
What if my computer is sad?
It's not worth the money to buy a expensive computer for the extra speed. So if you look at a i5 processor, like a really kind of common dual core, maybe not even 4-core i5 processor, it's not expensive by today's standard. But if you try to get a really high-end i7 processor, it's a lot more expensive. And most people think, but I'll be getting so much more processing power, this will last me longer. But that argument doesn't apply to the really high-end processors, because the way Intel charges charges you money for the processor is after a certain point it's no longer linear. To take the next step, it will cost you a lot more to gain that one little bit of performance. So to most people, it doesn't really make sense. Okay, so I took this little digression here, but now let's get back to this the gate stuff. Okay, so what I'm doing here is to say from here to here, in terms of time, there is a certain delay. Okay, it's in nanoseconds. Maybe even a fraction of a nanosecond, but there's still time in order for the input to settle from the time the input is settled to the time that the output is settled. Okay, this part is worse because it has to go through the NOT gate first, and then the NOT gate has to go through the AND gate, and then the output of the AND gate has to go through the OR gate to become the actual output. So there is 1, 2, 3. There are 3 delays in the second case. Okay.
Wouldn't you need to do both sides of that?
Say again?
You have to do.
But they're parallel. The 2 sides are parallel.
Oh.
Because when this is implemented in hardware, they are truly parallel. So you have this gate and this gate will be operating in parallel. So you still have only 3 levels of propagational delay. That is actually not true in either case, because inside the computer, for the most part, they don't really use OR gates and AND gates. They use NAND gates, NOR gates. There are gates that are more natural when it comes to making transistors to create gates. So they are not actually like this. But I'm just saying that just looking at it using the gates that we are familiar with. I like the screensaver, but it's distracting. This would take 3 times the amount of time for the propagational delay. What about this entire second column here? The second column, this half adder will have to wait, has nothing to wait. Okay, so this half adder here will only have a 3 times the propagational delay of 1 gate. But the second adder has a problem. The second adder cannot do anything until the result of the first half adder is done. Okay, so that's 3 units of propagational delay. And then the worst part is it has to take the carry of the previous one, which in this case is not too bad. Then it can do its own calculation, which means this carry here will have a 6 unit of propagational delay. 3 units of delay from here, and then 3 additional delay from itself. So it has a propagational delay of 6 units. And guess who's going to take this carry flag as an input? this junction here. So now we have what, 7 units of propagational delay. By the time it becomes the input of the next column, it's already 7 units of time, 7 units of propagational delay time from the entire bit pattern A, B, C, D, and E, F, G, H becomes stable. Are you guys getting the point here? So the further down or the more significant the digit, the more delay they have to experience, because they cannot do a single thing until the carry is propagated to those specific full adders. Is that okay? And this is proportional. If you're dealing with a 4-bit adder, if you're comparing a 4-bit adder to a 32-bit adder, the 32-bit adder is going to take pretty close to 8 times the amount of time of a 4-bit adder to settle. Okay, and now we have what, 64-bit processors, right? So that's going to take twice as long to settle compared to a 32-bit adder, and that's not acceptable. And it's way too slow. Okay, so what people actually do when they deal with adders inside the processor, multi-bit adder inside the processor, they do not rely on the carry flag to propagate. So what do you mean by it doesn't depend on the carry flag to propagate? What they actually do, okay, so let's take a look at this equation here. If you look at this equation here, let's look at the way we calculate the bit Q in this picture. So what you do is you look at n here, and you say, well, I'm not going to express n as this equation here. I will take this whole thing and expand it in place in here. But this entire thing also takes bit k, which is derived from something else. Well, that's fine. Take bit k and expand that entire thing in place. So you end up with one pretty gigantic equation, and then you simplify it. So when you simplify the equation, you are going to decrease the number of propagational delay because you're removing operations in between. Okay, so let's go ahead and do this once, just to see what we will end up with. Okay, so we'll start with this one here. There's no need to copy onto a piece of paper because it's going to be a little bit difficult to do on a piece of paper, and you'll see why. Okay, this is n here, and n is defined to be this mess here. Fine, we'll just copy and paste. And anything that is not A, B, C, D, E, F, G, H, we have to replace it until everything is expressed as A, B, C, D, E, F, G, H. Okay, it has bit k here that is not A, B, C, D, E, F, G, H. Okay, let's see how k is defined. K is defined like this. Replace it like this. Okay, so now I think we have A, B, C, D, E, F, G, H only. And then the next thing you do is you expand, the carry flag as a conjunction, and then the R flag as the way we define it. Okay, so you end up with one pretty long, logical expression, and then you look at the really long logical expression and you simplify it. And when you simplify it, you'll be decreasing the number of operators, and as a result, you'll be decreasing the propagational delay in order to come up with bit Q. It's not going to take the propagational delay of 4 full adders anymore. It's going to be a lot faster. And that's how actual processors are designed. They're not using this is what we call propagating a carry flag. In this case, there's no propagating of a carry flag. It is just calculated as one complex equation using bit A, B, C, D, E, F, G, H as input. Okay, let's count here. Let's make sure that we have accounted for all the bits here. We have A, B, C, D, and then we have E, F, G, and H. So in order to calculate bit Q, you can just take one gigantic equation, take all 8 bits that serve as the input to this 4-bit adder, and do it as one single expression. That's how a real adder is implemented in the processor. the other way that I showed on the whiteboard is easy to understand, but it's very slow in terms of implementation. This way, it is faster, but it is complex for a person to deal with. So how do you think Intel can do all this stuff with 32-bit or 64-bit adding? Remember, with a 64-bit adder, this equation will take 64 times 2, which is 128 variables as input. And then you have to simplify it. So does anyone want to do that job? Your only job is to optimize the adder. No, Intel actually doesn't do it that way. They have computers to help solve those equations and simplify those equations. Okay. Any questions about what we have just talked about here? What about subtracting? Now that we're done with adding, what about subtracting?
So what is like Q? Is it like what is it? Like you added the bits.
It is the last carry flag of the most significant column of your adding. It cannot be stored because when you're dealing with computer storage, okay, you're dealing with fixed width storing, right? It's either 8-bit, 16-bit, 32-bit, 64-bit. Okay, by today's standard, I'm pretty sure soon we'll have 128-bit stuff. But nonetheless, the input and the output must have the same width. You cannot say, well, the input is 8-bit, but I want to store 9 bits. No, the last bit, the most significant bit, has nowhere to go because every memory location has the same width. So that's why bit Q here is kind of like a carry flag that is floating around. It is not stored as a result, but nonetheless, it is available, it is accessible to the processor. The use of bit Q will be obvious later. In about 2-3 classes, it will be obvious what we use it for. Right. Now that we're done with adding, let's try to deal with subtracting. So we'll deal with subtracting kind of the same way. We'll start with something like this. Okay, we'll start with a table like this. So now we'll go to here, and then we have two independent inputs. Okay, bit X and bit Y are the input. We want to calculate what is X minus Y, and then we want to calculate the borrow of X minus Y. Okay, so we'll start with 0, 1. When X is 0, Y can be a 0, Y can be a 1. While X is 1, Y can also be a 0 or 1. Let's look at the result of the subtraction. And remember, this is from the perspective of a multi-column subtraction. Okay, 0 minus 0 is 0. What about 0 minus 1? It's a 1. Very good. 1 minus 0 is a 1. 1 minus 1 is a 0. That looks vaguely familiar. What about the borrow flag? 0 minus 0, does it generate a borrow from the next digit?
No.
Nope. 0 minus 1?
Yes.
Yep.
Yes.
1 minus 0?
No.
Nope. 1 minus 1? No. So the only time we have an actual borrow is this row here when we subtract a 1 from a 0. Okay. All right. So if we want to re-express this stuff here, this is, let's say we call this Rxy, or the result of X minus Y, I think we can just recycle what we had earlier because it looks exactly the same. 0, 1, 1, 0, and then if you go back here, it is 0, 1, 1, 0 as well. Okay, so we can just go ahead and copy this because we know this works. Everything around a little bit here. The borrow flag seems a little bit kind of difficult, but it actually is an easy one. Okay, the borrow flag is true only when X is a 0 and Y is a 1. So how should we express that?
Not X and Y.
Exactly. Okay, so it's just not X and Y. Well, let's double check, okay? On the first row, when x is a 0 or false and y is also false, this has to be false because in order for a conjunction to be false, you only need up to one side to be false. Okay? They can both be false, but if one side is false, the whole thing has to be false already. This is the row that we are interested in. X is false, not x is true. Y is true, so we have true and true, which is true. Okay? The third row has x being true, so not true is false already. One side of conjunction is false. The entire thing has to be false. We don't even bother to look at y. And the same thing applies here because x is true, not x is false. When the left-hand side of a conjunction is false, we don't even bother to look at the right-hand side. So it does implement exactly the same thing using one negation and one conjunction gate. And then the rest are pretty much the same. The way we stack things is pretty much the same way. In other words, if we just redefine R and, well, excuse me, if we just redefine C to the borrow flag, we can basically just reuse the structure that we have here and also reuse everything that we have here, but this time it will be for subtraction. All right. Are there any questions about how we do subtraction in binary? Any questions? Right. But since we're dealing with subtraction, sooner or later this question will pop up. What if we subtract something from 0? Okay, let's think about it. Okay, let's do some kind of easier subtraction first. So we'll deal with, let's say, this subtraction here, just to make sure that we understand how to do subtraction in binary. I'm going to do this the same way as we do the other ones. We'll have two rows, one row to represent the borrow from a previous digit. Okay, so this one is just 1 minus 0, which is a 1. Does it generate a borrow right here? Nope, so that's fine. And this bit is representing a borrow from a bit that does not exist because this column is already representing the least significant bit here. So this borrow is going to be a 0 because there's nothing that can borrow from this column. So we have now another subtraction, which is just this 1 minus this 0, and that will just make it a 1 with no borrow. Since neither of the subtraction generates a borrow, this borrow is going to be a 0. 0 minus 0 is a 0. 0 minus 0 is also a 0. And neither subtraction creates a borrow. So that means the borrow to the next digit is going to be a 0. But this time when we have 0 minus 1, we end up with a 1 and a borrow. So we put that borrow right there right away. 1 minus 0 is a 1. And then on the most significant column, we have 1 minus 0 being a 1. 1 minus 1 is a 0. And neither subtraction generates a borrow. So if we want to represent bit Q, it is going to be just a 0. Because the entire subtraction does not generate an overall borrow. Are there any questions about this representation of subtraction? Is that okay? Okay, so now we want to take a look at what happens when we subtract a value, a non-zero value from 0 itself. Oh wait, let's double check and make sure this makes sense. Okay, 1001 in base 2 is what in base 10? 9. And 0100 is 4. And just skip all the way to the end here. What is 101 in base 2? 5. So it's okay. Okay, just double checking. Do the base conversion for each number just to make sure that the result makes sense. Okay, so this time we're going to use something to subtract from a 0. And we'll just say, let's subtract 5 from 0 and see what happens. This is all in base 2. Okay. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow. 0 minus 1 is a 1 with a borrow. 1 minus 1 is a 0. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow. Okay. That's okay. I mean, I just did everything according to the rules that we have talked about. Okay. But what does that mean? What does it mean when 0, 0, 0, 0 minus 0, 1, 0, 1 is 1, 0, 1, 1? If you look at the base conversion, it doesn't seem to make any sense because we are saying that 0 minus 5 is this number here, and that number turns out to be 11. That doesn't make sense. Well, it doesn't make sense until you look at the bit pattern from the perspective of 2's complement. Okay. Now, this is the best way to look at this is to look at it as a wheel. Okay. When you can only have 4 bits, how many values can be represented? The first bit has 2 choices, 0 or 1. The second bit has 2 choices that is independent from the first bit, 0 or 1. The third bit also has 2 choices, but that's independent to the first or the second bit, right? So how many choices do we have, or how many combinations of zeros and ones can I have when I have 4 bits?
32?
16.
16. 2 to the power of 4 is 16. Okay? So I'm going to draw a picture of a wheel with 16 individual points. 4, 8, and then we have 16. Okay. So now we have a wheel of 16 individual points. So we have 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, and so on. And the last one is going to be 1, 1, 1, 1. Okay. Well, these are only bit patterns. Okay. The value represented by a bit pattern is not necessarily just based on plain base conversion. Okay. So one way to look at this is to say this is representing the value 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. In other words, with only 4 bits, we can easily look at that and say, oh, we can represent values from 0 all the way up to 15. But that's just one way of looking at this. Because if you look at addition as rotating this way and subtraction as rotating the other way, I can just as easily say that, hey, if you subtract 1 from 0, I should be getting -1. If you subtract 1 from -1, I should be getting -2, -3, -4, -5, -6, I skipped something.
You skipped 14.
Did I miss something?
Yeah, you skipped 14.
I skipped 14?
Oh, you did, yeah.
Okay, so -2, 3, 4, 5, 6, 7, and this one I'm not gonna say anything. So now we can look at these particular bit patterns here and say, I wonder how I should be looking at these particular bit patterns. Okay. If I look at the bit pattern 1, 0, 1, 1, I can look at it as 11 when I count in this direction, but I can also look at this as -5 when I count from the opposite direction, and saying this is 0 minus 1, 0 minus 2, 0 minus 3, 0 minus 4, and 0 minus 5. And it seems to make sense to look at this bit pattern here, 1, 0, 1, 1, as -5 because it is the result of 0 minus 5. Is that okay so far? Okay. How many people still remember in C++ programming, you can say an integer is signed, just int, or it can be unsigned? Okay, you still remember that? That's basically what this is. Okay, it's the same 16-bit or 32-bit or 64-bit. The question is, how do you interpret the bits? Okay, so for half of this wheel, they can be representing positive numbers. For an unsigned interpretation, they can also be representing negative values for a signed interpretation. Okay. Now in C, C++, the interpretation is based on the type. Okay. When you say something is unsigned, then it is being used as an unsigned number. When do you think that matters? Whether something is signed or unsigned?
You're adding or subtracting.
That is actually when it does not matter. Because look at the way we do the subtraction here. I did not use anything special to come up with this answer here, even though in signed interpretation, this makes sense, right? So addition and subtraction, the way we perform our bitwise addition and bitwise subtraction can apply to signed or unsigned interpretation. It doesn't matter, okay? When do you think in C and C++ programming that signed versus unsigned makes a difference?
When you're trying to make your program as small as possible.
Okay. What about comparison? That would matter, wouldn't it? Okay? Because when you're comparing, then you have to ask the question. Okay, so let me just give you this question here. I have the bit pattern 1101 here. It's a base 2 number. And I want to see if this is actually less than 0, 0, 0, 0 in base 2. That's the question. Is that true or false? Well, you have to know, is this an unsigned number or a signed number? Right? Because if you look at 1101 as a unsigned number, it is representing what value? 13. It's representing 13. Okay? 13 is less than 0 is false. But when you look at it as a signed number, what is it on that wheel?
-3.
It's representing -3. -3 is less than 0 is true. Okay? So the only time, well, I shouldn't say the only time, but one of the more important moments when signed versus unsigned interpretation is important is in a comparison. The other time would be in the division and the multiplication, because those are also sign sensitive. Okay? But addition and subtraction, surprisingly, are insensitive to whether a number is a signed number or an unsigned number. Okay? But that is also called 2's complement. Okay? Let's look at the 2's complement. I'm just going to expose you to the concept and then we'll end today's class. 2's complement, I just use C2 here as the representation. If you define C2 as a function as 2's complement and apply it to bit pattern x, it is the same thing as taking 1's complement of x and just add 1 to it. In C, C++, what is the bitwise not operation, which is also known as 1's complement? Which symbol represents the bitwise not operation?
The caret symbol.
It's the tilde.
Oh.
The tilde symbol in C and C++ represents negation, bitwise negation. Okay, let's see whether this makes sense. Okay, we'll just do one double check and then we'll end today's class. And then we can move on to the lab. So for those of you who have not done your virtual machine homework assignment, we can go to the lab and we can get it done over there. So we'll just take one example here. Guess what? I'm going to use 0101. Okay, because we have done it already. So we want to apply 1's complement, which is just a bitwise not, to 0101 and then plus 1 to it. 1's complement is basically flipping all the 1's to 0s and flipping all the 0s to 1's. So this one becomes 1010 plus 1 in base 2, and it becomes 1011. Haven't we seen this before? We are taking the negation of 5 and we're ending up with -5. Seems to make sense. Let's see if we can do it the other way around. In other words, if we take the negation of 1011, which is representing -5, we should get 5 back. Let's see. Flip all the 1s into 0s and all the 0s into 1s. So this becomes 0, 1, 0, 0 plus 1. And it does get back 5. In other words, if you look at these operations using 2's complement, it is as if it is the same thing as an arithmetic negation or inversion. Negation. Is it called negation when you subtract something from 0? I think so. Yeah, but it serves the same purpose. And this is called 2's complement. This is how negative numbers are represented using only 0s and 1s. Because when you look at the memory of a computer, it doesn't have one bit just to store the sign of a number. Okay, this is how a negative number is stored. The one last thing, I know I'm already running overtime here. This table doesn't seem symmetric because if you look at negative numbers, they only go from -1 up to -7. But when you look at positive numbers, it goes from 1 to 8. We're forgetting one thing here. We're forgetting 0, aren't we? If you count the number of negative numbers versus the number of non-negative numbers, they are exactly the same. Actually, it's not balanced now. Now it is. How many non-negative numbers do we have on this field here? Using the inner circle, we have 8 because it's going from 0 to 7. How many negative numbers do we have? Also 8. Okay? Because if we don't do this, then it's not balanced. This is the balanced way to do it. And then if you look at all the negative numbers, what is common of all the negative numbers? What is the one thing that is always there for all the negative numbers? The most significant digit is always a 1. That's why it's also called a sign bit. Okay. So we'll come across these concepts again later on in the semester. So for the time being, there's no homework assignment for numbers, addition and subtraction. There's still just that one assignment for getting the Linux environment up and running. And I forgot to pass the row sheet again. I got it all printed, but I forgot to pass it around.